Welcome back. This is lesson 23, and today we're stepping into one of the most important shifts in modern networking, IPv6. Over the next few slides, we'll unpack what 128 bits really means, how those addresses are written in hexadecimal, and most importantly, why IPv6 had to exist in the first place. Let's get into it. Here's the path we'll walk together. First, we'll look at the math behind IPv4 exhaustion, the simple but striking numbers that forced the industry's hand. Then, we'll meet the 128-bit address itself and the hexadecimal notation that makes it readable. From there, we'll learn the compression rules that shrink those long strings down to something manageable. And finally, we'll break an address into its two meaningful halves, the prefix and the interface ID. So let's start with that math because it really is unforgiving. IPv4 uses 32 bits, which gives us about 4.3 billion addresses. And that sounded enormous in the 1980s, but we passed 8 billion humans years ago. Never mind every phone, server, and IoT sensor each one carries. IANA handed out the last blocks back in February 2011, and NAT has been quietly papering over the shortage ever since, buying time, but breaking end-to-end connectivity in the process. IPv6 jumps to 128 bits, and that's not just 4 times bigger. It's 3.4 times 10 to the 38th, roughly 50 billion addresses for every person alive. Enough, quite literally, to label every atom on the surface of the Earth. So, how do we actually write a 128-bit number? We break it into 8 groups of 16 bits, and each of those groups gets expressed as 4 hexadecimal digits separated by colons. Take this classic example, 2001, ODB8, 85A3, and so on. That's 8 blocks, 4 hex characters each, giving you all 32 digits and all 128 bits. Hex is case insensitive, so uppercase or lowercase makes no difference, and technically all 8 groups must be present. Though, as you'll see next, there's a shortcut for those long runs of zeros. Before we go further, let's make sure hex itself feels comfortable. Each hex digit maps cleanly to exactly 4 bits, which is why it's perfect for IPv6. 1 digit covers 4 bits, 4 digits cover 16, and that's one full group. The digits run 0 through 9. Then A through F for 10 through 15. And once you pass EF, you simply carry. So F plus 1 becomes 10. With this table in your head, a chunk like 8A2E instantly unpacks into its binary form, and the rest of IPv6 starts to read naturally. Now, writing out all 32 hex digits every time would be exhausting, so IPv6 gives us 2 compression rules. Rule 1, inside any group, you can drop leading zeros, so 0db8 becomes db8, and 0042 becomes just 42. The group still holds 16 bits. We're only hiding the zeros at the front. Rule 2 is more powerful. A run of consecutive all-zero groups can collapse into a double colon. So 2001 8 shrinks all the way down to 2001 db8. 1. The critical catch. You can only use that double colon once per address. Use it twice, and there's no way to know how many zero groups belong on each side. So, by convention, you apply it to the longest run. Let's put those 2 rules to work. In the first row, 2001, db8 loses its leading 0 to become 2001 db8, and the 6 zero groups in the middle collapse into a double colon. The FE80 link local address works the same way. One long 0 run becomes that double colon. Notice the loopback and the unspecified address. All zeros except a trailing one becomes simply : 1, and all zeros collapses entirely to : But watch the last row carefully. There's no run of 0 groups, so there's nothing to compress with rule 2. You still drop the leading 0 from 0db8, but the double colon never appears. Now that we can read and compress an IPv6 address, let's look at how it's actually structured internally. Almost every IPv6 address splits cleanly down the middle. The first 64 bits identify the network, and the last 64 bits identify the specific interface on that network. The prefix is what your ISP hands you, or what your network design dictates, and it stays the same for every device on that subnet. The interface ID is where the host lives, and with 64 bits to play with, that's roughly 1.8 times 10 to the 19th possible hosts per single subnet, far more than you'll ever need. It can be set automatically through SLAAC, handed out by DHCP-v6, derived from the MAC address using EUI64, or randomized for privacy. With that structure in mind, IPv6 actually defines several types of addresses, each with its own job. Global unicast, starting with 2000, is your public, internet routable address. Unique local, the FCRO range, usually written as FDAROB, is the private equivalent, like the old 192.168 space. Link local, beginning with FE80, is auto-assigned and required on every interface for local communication. Multicast replaces broadcasts entirely, and you've still got loopback and an unspecified address for special cases. The key thing to internalize, every interface carries at least two addresses simultaneously, a link local and a global, and that's completely normal in IPv6. Now it's worth stepping back and seeing just how much changes between IPv4 and IPv6, because it really isn't just a longer address. The header is fixed at 40 bytes instead of variable, which means routers process packets faster. Broadcast is gone entirely, replaced by smarter multicast. Routers no longer fragment, only the sender does, using path MTU discovery. The header checksum is removed because layer 4 already handles it. And NAT, that workaround we lived with for decades, simply isn't needed anymore. So IPv6 is genuinely simpler under the hood, not more complex. And the best way to make all of this concrete is to actually look at IPv6 on your own machine. On Linux, IP6adder show lists every IPv6 address on your interfaces. You'll typically see two, a global one starting with 2001 and a link local one starting with FE80 that exists on every IPv interface automatically. Add the 6 flag to ping or tracer out to force IPv6. And if you just want a quick yes or no answer, curl the ISO and has a IPv6 endpoint. If it returns an address, you're already on the new internet. So let's pull everything together. IPv6 is 128 bits, written as 8 groups of 4 hex digits separated by colons. And you compress it by dropping leading zeros and collapsing the longest run of 0 groups with a double colon, used only once. Almost every network you'll meet splits cleanly into a 64 prefix and a 64 interface ID. Remember the prefixes: 2000 for global, FE80 for link local, FCA0 for unique local, FORO for multicast, and forget broadcasts entirely. IPv6 uses multicast, and every interface happily carries several addresses at once. And here's your cheat sheet, a single page to keep nearby while the concepts settle in. Everything we covered is here: the size, the format, the 2 compression rules, the standard 64 to 64 split, and the prefixes for each address type. One small addition worth noting: the loopback in IPv6 is simply : 1. The direct equivalent 27.0.1 in IPv4. Screenshot this, print it, keep it open in a tab, whatever works. And that wraps up lesson 23. In the next lesson, we'll pick up exactly where this one leaves off, moving from how IPv6 addresses are written and structured to how they're actually assigned and deployed. We'll cover SLAC, the mechanism that lets devices configure themselves automatically, dual stack networks running IPv4 and IPv6 side by side, and the practical realities of migrating from one to the other. See you in lesson 24.